Okay, all right. And yes, we measure time. We measure time using a notation called as asymptotic notation. Asymptotic notation, right? Asymptotic notations. Okay, and there are a lot of asymptotic notations, but the most popular one is big O. Big O. Okay, the most popular one is big O, which is given by this syntax. So big O of something, and this will contain the order. Okay, and mostly in terms of n log, and I'll tell you that. Okay, I'll tell you how to find the big O notation, right? So based on this, this will tell you the complexity of the algorithm, the time complexity of the algorithm, right? And again, don't confuse yourself. This is just a notation. That's it. Okay, just the notation to express the time complexity. This is for time complexity. Okay, okay. And we don't much consider the space complexity. We will mostly concentrate only on the time complexity. Okay, so that's the big O notation. All right. Okay, let me tell you how to find big O for a particular algorithm, right? So there are a lot of types of big O notation. Okay, one is constant time complexity, which is given by big O of 1. Okay, very efficient, very efficient, right? Constant time complexity. Okay, and next one is linear time complexity, which is given by big O of n. Third one is uh, quadratic time complexity. Before that we have logarithmic. Okay, that is way more efficient. Okay, so logarithmic time complexity, which is given by big O of log n. It is even more efficient than linear, guys. So what I could do here is, let me put logarithmic in front of linear, because it's even more efficient than uh, linear. Okay, so logarithmic is more efficient. So logarithmic is O of log n. Third one is linear, of course. Linear is O of n. All right. Fourth one is, yeah, let me go for linear logarithmic. Linear logarithmic, which is O n into log n. Okay. Fifth one is quadratic. Okay. Which is not a good time complexity, guys. Okay. Quadratic time complexity is not so desirable, right? So next one is cubic time complexity, O of n cube, and I can also go for exponential time complexity, which may be O of 2 power n, O of 3 power n, and big O of 4 power n, so and so, right? And the last one would be factorial time complexity, which is very worst. Okay, O of n factorial, right? So I have written in the order of efficiency. So you can see that constant time complexity is way more efficient than logarithmic, right? And logarithmic time complexity is way more efficient than linear. Okay, so I've written in that order, and I would suggest you to note these all down. If you are seeing this for the first time, please note this. I think you have to be familiarized with this. Okay, so yes, let me explain the meaning of it. Okay, if I say O of 1, it means that the program, say for an example, I'm telling that the time complexity of the program is O of 1, right? Which means that the program will take constant time. Okay, the program will take some constant time to execute, but I don't know the constant. Okay, it may be 5 units, 6 units, 7 units, even 50 units, but I don't know the constant, but it will take some constant time to execute. Okay, and that is denoted by 1. This 1 doesn't mean that it will take 1 unit of time. It doesn't mean that. This 1 denotes the constant unit. Okay, so so O of 1 means the program will take some constant units of time. It may be 11, 12, 13, any constant number, but it takes constant unit of time. And if I say O of log n, this means that the program takes log n units of time. What do you mean by n here? What does n denotes here? Okay, n is nothing but the size of your input. size of the input that you are giving. Okay, and that is customizable, right? So you can give 5 inputs, 6 inputs, and that depends on, let's say I am using an array. Okay, let's say I'm using an array. uh, n is the size of the array. Then it is O of n means that time complexity depends on the size of the array. If the size of the array is very small, then the time complexity will be very small. Otherwise, it will be longer. Okay, that's how it goes on. N is nothing but size of the input, right? So log n means log will always convert higher values to smaller values, right? That's how it works, right? Higher values to smaller values, roughly. Okay, I'm not you know asserting that, it's roughly. Okay, as it's always somewhat converting higher values to I mean smaller values. So log of the size of the input. Okay, so it will convert uh, it will execute that time. So let's say my size is 5, n is 5. So what is log 5? Okay, log 5 is, I think, 0.698. Okay, so it's very small, right? So this program will go that times. Okay, this program will execute 0.6989 units of time. Okay, that's how it works. So log n is way more efficient than linear, right? So linear is of n. Let's say my n is 5 there, then the program will execute 5 times, right? So O of n, then O of log n, O of n log n, O of n square, it goes on like that. And these are all undesirable time complexities. Okay, quadratic, cubic, exponential, factorial, these are not desirable, whereas we always look for linear, logarithmic. Okay, a good program is something that has linear and logarithmic time complexities. Say for an example, you are writing an algorithm to solve a particular problem, right? Say for an example, and the time complexity of your algorithm is linear time complexity. Okay, often. And if somebody writes this another algorithm to solve the same problem, but their time complexity is O of n square, quadratic, then your algorithm is way more efficient, right? Because it takes only linear time, right? And that's how it works. I hope you have understood that, and how to find the time complexity of the algorithm, and that is the crucial part of this lecture. Okay, so let me teach you that. All right.